Okay, welcome to IIT Bombay Commutative Algebra Seminar. We are delighted to have Professor Graham Leuschke from Syracuse University. Graham is known to many of us through his two excellent books published by AMS. In fact, the book on 24 hours was a basis of two workshops in India, and many of us have learned many things from that book. And the other book is on maximal Cohen-Macaulay modules, and today's talk will have many things from that book. We are looking forward to his talk. The talk will be for 1 hour. At the end of 1 hour, we will have question-answer session. But of course, you can interrupt in the middle through the chat box, and I will relay your question to Graham. We are very delighted that Graham, in spite of his duties as chairman of his department, he has found time to speak to all of us. We thank him for that. So we now invite Graham for his seminar. Yeah.
Thank you so much, Jugal. That's very kind of you, and I appreciate everyone coming today. Hello from snowy Syracuse.
Yeah.
So my goal for today is to give some background. Most of the first half of this will be sort of old material from the 1900s. So I want to explain what a matrix factorization is, and following Eisenbud, and then to describe a result of Knorrer about relating. So I'm going to go ahead and write something here. So this is just kind of background sketching. So the result of Knorrer that I want to mention is relating matrix factorizations, whatever those are, I will tell you, of f and of f plus z squared, where z is some new variable. So that will be the first half, or maybe 2/3, and then at the end there will be a bit of new material which are all due to my PhD student, Tim Tribone, who I think is here. I saw a minute ago. Hi, Tim. Good morning. Good evening to everyone else, but good morning to Tim. So that's the plan. And let me start now by making one observation. So the observation is that the polynomial xy plus z squared is always irreducible over any field, as long as you rule out characteristic 2. This polynomial can't be factored in any non-trivial way. But if you, instead of wanting to factor the polynomial itself, you ask to factor the 2x2 matrix with the polynomial xy plus z squared on the diagonal, this factors. You can probably see what it factors as faster than I can make sure I get the signs right. This factors like so. Let's see, I think I just need a sign here and a sign there. That's either right or off by a sign. In either case, it certainly is a true fact that this is a factorization not of xy plus z squared, but of this matrix. We call this a matrix factorization. So this was known already to more or less this was known already to Dirac in the 1930s. Though he actually, he did more than just factor a polynomial in matrices. He took a square root. So a slightly special case. But so let me go ahead and define explicitly what we're talking about here. So And this is going to be notation in effect for the rest of the talk. We're going to let S be a regular local ring. It's actually not necessary that S be regular local for a lot of what I'm saying, but I'm just going to fix this notation in this setting once and for all. And let's take some polynomial or some element, some ring element F in this regular local ring. I'm always thinking that it's a polynomial, but then a matrix factorization and I will often abbreviate MF, is a pair of matrices. Traditionally, phi and psi, so that, well, first of all, they have to be of appropriate sizes that you can multiply them in either order. So, of course, they have to be square. And when you multiply them in either order, you get the diagonal matrix with F on the diagonal. And, of course, zeros everywhere else. So this is exactly what we saw in the example above. Now, aside from being Dirac and wanting to take a square root of the Laplacian, why would you care about such a thing? So let me relate these to modules. That's the primary connection for me. So since we're working over a regular local ring, so in particular it's a domain, so in particular F is a non-zero divisor. Since F is a non-zero divisor, both these matrices, phi and psi, are one-to-one, or multiplication by these matrices is injective. So in particular, we get a short exact sequence multiplication by phi is injective, that's the zero, and then here, well, it's just the co-kernel. And try to keep this this equation on the screen because it's sort of the source of everything. Because of this equation, you can see that F of S to the n, I'm thinking the middle term in my short exact sequence here. So this is, I'm writing it as if it's F of S to the n, but really it's F times S to the n. That is, well, F is phi psi. So this is contained in the, contained in the image of phi. So what that means is, in terms of the co-kernel, F kills the co-kernel of phi. That means that the co-kernel of phi is naturally a module over the hypersurface ring which I'm going to always write as R. So what happened here? We took a matrix factorization, and the co-kernel of one of the matrices is naturally a module over this hypersurface ring R. Now, Jugal mentioned the phrase maximal Cohen-Macaulay modules. I know I've seen many of you at conferences, and we've sat in the same talks. You know that these are one of my very favorite things. So let me remind you what a maximal Cohen-Macaulay module is, because co-kernel of phi is one. So I'll call this a recall, though you don't have to have seen it before. I will do my best to explain it. So two things. First, a finitely generated module let's say M over a ring, and let's say a local ring A, Noetherian always. A finally generated module M over a local ring A is called maximal Cohen-Macaulay. Again, I'll abbreviate this, MCM this time. If its depth as an A module is equal to the dimension of A. So if you haven't seen the phrase depth before, it's I'm going to not go into the background on this. Let's just say that depth is an arithmetic measure of torsion freeness. So high depth means that the module is very torsion free, and that this this value, dimension of A, is the max possible. So these modules are extremely torsion free as they could possibly be. And secondly, also about depth, this is the Auslander-Buxbaum formula, which I'll just remind people quickly. That if the projective dimension of M over A is finite, then this depth in the remark above is equal to the depth of A minus the projective dimension of M. So, with those reminders in place and looking back at this short exact sequence here, this one right here, the co-kernel of phi, as we said, it's an R module. It has projective dimension 1 over S. Whoops. Projective dimension 1 over S will mean down here, this will be a 1. That will let us compute the depth of M. Depth doesn't care whether you measure it over S or over R. So the upshot of all of this, and I'm glossing over a couple of details, but the upshot of the whole previous slide, 2 slides basically, is that the co-kernel of phi is a maximal Cohen-Macaulay R module. So that's extremely exciting for me. That's where I get excited. And conversely, any maximal Cohen-Macaulay R module, again by Auslander-Buxbaum, has projective dimension 1 over S. So it has a free resolution that looks like, well, it looks very similar to the one I drew above. And then the trick here is that multiplication by F kills M, because we're assuming that M is an R module. So is homotopic, homotopic to 0 on this complex, on this free resolution. And if you write down what that means, what a homotopy of F on this resolution is, it's a map backwards from Sn to Sn, which maybe we will call psi, and for it to be a homotopy means exactly that, have I got the, yes, the order is right there, means exactly that the composition or the product of the matrices is multiplication by f. And then because phi is injective, you can check that the other order, the multiplication in the other order, is also multiplication by f. So what we've done here, what we've proved, is a theorem due to Eisenbud, which appeared in 1980. Which is that the correspondence between a matrix factorization and the co-kernel of, let's just say the first matrix, we could pick either one, but the first matrix, this defines a bijection between, whoops, here's a word that I haven't defined yet. I'll have to define it in a second. Reduced matrix factorizations of F and I need to insert here one other thing as well, up to a natural equivalence relation. And maximal Cohen-Macaulay modules over R without free summands. So this is, we haven't really proved all of Eisenbud's theorem. There are statements here that I haven't even defined. So let me at least make sure to define this word, which will also give me an opportunity to give an example, kind of a trivial example, but anyway. But we haven't proved this whole thing, but this is really the foundation of interest in matrix factorizations. So to talk about reduced, let's look at two, they're sort of examples, they're sort of just generic. So what's the first matrix factorization you might think of? It's, well, F and 1, the ring element 1. So these matrices are 1 by 1 matrices. Or you could, of course, do it in the other order. So what do these relate to? Well, the co-kernel of F, co-kernel multiplication by F, that's just R, that's the ring, S mod F. And what's the co-kernel of the other one? Oh, co-kernel of 1 is 0. So these ones are clearly, they always exist. And if we're going to have something in the theorem about avoiding free summands, then we clearly need to avoid the first one. And that's what the word reduced does. So we say phi psi is reduced if it has no summand, direct summand, isomorphic to either of these. So these ones are in some sense trivial, and those are the ones that Eisenbud's theorem throws out. Let me give you an easy application to explain why matrix factorizations are in some sense more tractable than maximal Cohen-Macaulay modules. They're at least something you can compute with. You can do linear algebra. Linear algebra is the most powerful tool in commutative algebra. So first of all, here is just about the smallest ring we can consider. And it's also one of the easiest to deal with. This one, we know that the only indecomposable modules finally generated are the ring itself, so this is R, and the residue field K, where you kill X. So these correspond to the matrix factorizations, x squared comma 1, that's the free module as we saw in the example above, and the matrix factorization with co-kernel K is x comma x. In other words, these are the only indecomposable matrix factorizations. So you don't need, I mean, this is an easy exercise, but what about this slightly more complicated ring? It looks very similar. So what are the maximal Cohen-Macaulay modules over this ring? Now we have to say maximal Cohen-Macaulay modules because this one has some torsion modules and some torsion-free modules. Well, with the matrix factorizations, you can actually do the linear algebra, which is what Buchweitz, Groyle, and Schreier do in their paper in '87. And they say that the only indecomposable maximal Cohen-Macaulay modules over this one-dimensional hypersurface ring are the ring itself. So now this one's now called R. The ring mod X, just like before, and an infinite series probably not one, probably zero, or there we go, one. An infinite series of maximal Cohen-Macaulay modules given by the co-kernels of these matrices. And you can see where these come from, that there's another matrix that looks very similar to this one, giving a matrix factorization of x squared. So without matrix factorizations to do the computations for you, it would be very difficult to classify the maximal Cohen-Macaulay modules over this ring. But with them, it's linear algebra, as I said. Here is another sort of new viewpoint opened up by matrix factorizations. And I'm going to go ahead and I'll call this a new phenomenon. It still feels new to me, though I've known it for close to 20 years. Given two matrix factorizations, so let's say phi psi of f, and then let's take a different, I'm going to call it phi prime psi prime of g. And I want f and g to have nothing to do with each other. I want them to live in different sets of variables. Or disjoint. Maybe disjoint is a better word. So I think that maybe f has some x's in it and g has some y's in it. That's the idea. Then from this data, we can write down I'm going to make sure I follow my notes here to get the signs right this time. Sorry, one moment. There we go. So if I've copied my notes correctly, and if my notes are correct themselves, fingers crossed, this is a matrix factorization of the sum f plus g. We think of these as block matrices. And so these are now in the combined sets of variables. So for example, this might be, f could be x squared and g could be y squared. This would be x squared plus y squared. Yoshino, who I believe was the first to define this, calls this the tensor product. And his notation is, here's one matrix factorization, here's the other one, b prime, psi prime. The notation is tensor product with a hat. And he proves several different properties of this and some situations where it preserves indecomposability. He does a lot of really interesting things with it. It's important, though, to point out that while it's called the tensor product, and while it does do a thing that we're used to tensor products doing, that is take two modules on the Maximo-Cohen-Macaulay side and combine them to get another module, it's important to keep in mind that this construction has nothing to do with the usual tensor product of Cohen-Macaulay modules. So you could also take the co-kernel of phi and you could tensor it with the co-kernel of psi over, or not psi, phi prime, excuse me, over some ring with combined sets of variables. But the tensor product of Cohen-Macaulay modules is almost never Cohen-Macaulay, and it certainly doesn't relate to this tensor product of matrix factorizations. So this is something genuinely new, some new way to combine modules and get another module that we only found because of the matrix factorizations. So the mathematical physicists love this. I went some years ago to a week-long workshop in Oberwolfach consisting of mathematicians who like matrix factorizations and physicists who like matrix factorizations. And we spent a week speaking the same language and failing to understand each other. So let me give you a special case that's maybe easier to wrap your head around. Let's take the special case when g, that is the second variable, is z squared. So z is just one variable that's separate from all the other ones you might consider. So here's what I'm thinking. I'm thinking that there is our hypersurface ring R, which is S mod F, and then there is a hypersurface ring you get by adding on a new variable, and then here is F plus G, that is F plus Z squared. So this thing I'm going to denote R hash, or R sharp sometimes. And this is usually called the double branched cover for geometric reasons that I won't go into right now. And in this case, the tensor product construction that I sketched above takes a matrix factorization. Oh, so here's some notation I haven't introduced yet, but maybe it's sort of clear what it means. These are matrix factorizations of F. And it sends it to, well, the tensor product with the hat of some matrix factorization of G. Well, actually, we saw earlier that if you have only one variable, there are only two indecomposable matrix factorizations of that variable squared. One of them is just z squared comma 1. The only interesting one is z comma z. So let's use that one. And I won't scroll up and show you the formula again, but I'll write down what this is. This is the following matrix factorization of f plus z squared. So this gives you a machine for taking matrix factorizations of f and getting from them matrix factorizations of f plus z squared. And I'm being a little bit sloppy here. Of course, what I really should be writing is these are block matrices, Zi, where I is the identity matrix of the same size as phi, and so forth. But let me glide past those details. So this is a tool for getting, as I said, matrix factorizations of f to matrix factorizations of f plus z squared. What happens on the module level? That is, when we go from matrix factorizations to their co-kernels, as Eisenbud tells us to, what does this functor, this tensor product, do? And I'm actually just going to tell you and not try to justify. This is actually the first syzygy. So I'm going to use omega for the first syzygy. So this co-kernel of phi is an R module. R sharp, remember, it's up here, maps to R, so we can consider any R module as an R sharp module. And what this says is that this operation, this tensor product, is the same thing as taking a syzygy of the co-kernel of phi. We also have a reverse functor going from right to left. That is, going from R sharp modules to R modules by just killing Z. So what we have now is a way to get from R modules to R sharp modules, and also a way to get back. And in these terms, Knorrer's periodicity result looks like this. So I'm going to write three statements here, A, B, C. And they are what happens when you compose these two functors in either order. So in symbols, if I've got a matrix factorization of f, I can tensor it with z comma z, as I did, and then I can kill z. So I'm using bar to mean this going from R sharp to R by setting Z equal to 0. And it's actually not so hard to observe that this is the direct sum of the original one you started with and its syzygy, its what do you call it? Switch. You can actually do that straight from the formula that I had, let's see, right up here, right? So if you kill Z, what you get is the direct sum psi phi on the diagonal here. What about the other direction? So I'm going to use capital Greek letters for matrix factorization of f plus z squared. So what if I take a matrix factorization of f plus z squared, I kill z, and then I tensor with z comma z? Then it's the same phenomenon. I get the original one back, direct sum, same thing in the other order. So this pair of functors going back and forth, either composition gets you back to where you started, but not on the nose. You get where you started, direct sum, its syzygy. And as a consequence of that, Knorrer proves or observes that f has only finitely many indecomposable matrix factorizations if and only if the same is true of f plus z squared. And this is one of the main ingredients in the complete classification. So I'm going to leave a little space here. Whoops, what just happened? Oh no, disaster. That was close. So this is one of the main ingredients in the classification of hypersurface singularities of finite Cohen-Macaulay type. Complete hypersurface singularities over a field of, over an algebraically closed field of characteristic 0. Let me not stick all the assumptions in there. But that's what Knorrer was aiming for here. And I left a little space here because I want to make sure to mention that statement C here, the third statement, fails, and doesn't just fail, but fails dramatically, fails badly, if you try to add any other power, any higher power of Z. That you can start with f that has only finitely many indecomposable matrix factorizations, like, for example, x squared, as we saw, and you can add z cubed and suddenly have infinitely many. Add z to the fourth and you can have uncountably many. So this is something that's interested me for several years, to try to make some kind of statement about f plus z to different powers to achieve an analog of Knorrer's result. And this is something that Tim has recently done. So the last thing I want to say about Knorrer before getting to Tim's stuff, which I won't have time for very much of Tim's stuff, sorry Tim, but in order to contextualize it, the last thing I want to say about Knorrer is that the key ingredient, let's go back and use green, green better. A key ingredient.
Excuse me, sir. I think there is a question in the chat box.
Oh, okay, sure, what's up?
Yeah. So the question is, does indecomposable matrix factorizations mean the corresponding maximal Cohen-Macaulay module is indecomposable?
Yes, it does. I mean, so I guess that's more like a lemma rather than a definition. You can define the direct sum of matrix factorizations without ever mentioning their cokernels. And then you can say matrix factorization is indecomposable if it can't be written as a direct sum. And then you prove a little lemma that says that the corresponding Cohen-Macaulay modules are indecomposable. That's true as long as it's reduced, as long as it doesn't have f comma 1 or 1 comma f in it.
Thank you.
Okay. Where was I? Oh, right. Key ingredient for Knorrer's result that I mentioned above is a non-commutative ring. So Knorrer related matrix factorizations of F with what's called the skew group algebra, skew group ring, R sharp bracket sigma. So let me tell you what these things are. So here, so as always, R is S mod F. That's been in place the whole time. R sharp, we decided, was the hypersurface ring defined by F plus Z squared. And sigma, that's the new piece here, is an automorphism of R sharp, which, how can you define an automorphism of R sharp? Well, fix everything in S and send Z to minus Z. And then this skew group algebra, R sharp bracket sigma, has elements of the form A times 1 plus B times sigma with sigma squared equal to 1, so that tells you how to multiply the sigmas with each other. And here's the non-commutative part. Sigma times A, you can move the sigma past at the cost of applying it to the element A. So if you haven't seen this before, it can be sort of a lot to do all at once. But the upshot is that this is a non-commutative ring built from the double-branched cover that uses this natural automorphism that comes sort of naturally from the definition of the double-branched cover. And what Knorrer shows again, this is a theorem of course, Knorrer, is that there is an equivalence of categories. You can just think of it as a bijection if you like, between matrix factorizations of F and maximal Cohen-Macaulay modules over this non-commutative ring. So you may be wondering, what's a maximal Cohen-Macaulay module over a non-commutative ring? By definition, these are the R-sharp sigma modules that are free over S. So notice on the left-hand side, there's no z squared. This is just a ring element f that's handed to you. On the right-hand side, there is a new variable z. There is a new hypersurface f plus z squared, and there's this new automorphism sigma. So the moral here, I'll tell you how this equivalence works in just a second, but I'll tell you how I think about this result first. The moral is that the matrix factorization of f already know about the double-branched cover. Right? Because on the left-hand side of this equivalence, you see matrix factorizations. On the right-hand side, you see something involving the double-branched cover. So this has always fascinated me, that how do matrix factorizations of f already know about f plus z squared? So let me, well, I think I won't tell you how this equivalence works. It's fairly, well, it's not so hard, but it would take a little while for me to go through here, and I want to make sure to say some other things too. So I think that's enough for now. Because now I want to, mention some new work, new results. Of Tim Tribone, which are not on the archive yet, but maybe later today. Tim? We'll see. So what Tim has done is to consider now, instead of matrix factorizations, to consider d-fold matrix factorizations. That means matrix factorizations with more than just two matrices in them. So that's a d-tuple of matrices, all of the same size, so that, and you have to make some choice here for how you're going to multiply them. I'll just do it in this order, so that when you multiply all d of them together, you get f times the identity. So this is a fairly natural generalization of Eisenbud's matrix factorizations, and this part isn't new with Tim. As far as I can tell, these were first, well, maybe first considered in a paper of Bakelin, Herzog and Sanders. Though actually, this, I forgot to write down the date. I think this is in the early 90s-ish. But actually, Lindsay Childs in 1978 did something sort of like I described Dirac did at the beginning of the talk. He considered d-th roots of polynomials rather than arbitrary d-fold factorizations. He wanted d-th roots. So these are certainly considered in this paper of Bakelin, Herzog, and Sanders. They were interested because they correspond, let me say it like this. If f is homogeneous of degree d, the same degree as the number of matrices, then each of these, sorry, let me say it like this, each of the matrices is linear. That means has only linear entries. And they were interested in this because that means that the co-kernel of each matrix is an Ulrich module. And they were interested in constructing Ulrich modules. So we're not going to worry too much about linear entries. We're just going to consider matrix factorizations with more than two factors. All right, so a couple of quick observations about these things. First of all, given any sort of normal matrix factorization, so now this should be called MF2. So given a classical or normal matrix factorization, we can always inflate it by just adding on identities. As many as we like. So I write 1 here, but really I mean the identity matrix of the appropriate size. These are boring. Let's declare from the outset that those are boring. Okay, so the very next question should be, are there non-boring ones? Yes. Something like x comma y comma z is a triple matrix factorization of the product x times y times z, and it's not boring because it doesn't come from inflating a 2 matrix factorization. All right. What else? We can go the other way. If we have a d-fold matrix factorization, we can collapse it. That means just multiply all of the matrices except the first one together, get one single matrix, same size of course, and this now is in MF2. This is a usual matrix factorization. So we can go back and forth, and this is useful for inductive arguments. So what does this mean in terms of the modules? This collapsing business. This corresponds to extensions of the maximal Cohen-Macaulay modules. So for example, when, I'll make this an example. If you've got a triple factorization, then you collapse it to phi1 and then phi2 times phi3, and that gives you a short exact sequence like so, where I'll just point out that this is actually the syzygy of the co-kernel of phi1. So this involves each of phi1, phi2, and phi3. And of course, if you've got more factors and you collapse in different ways, you get different extensions. You get some sort of filtration. All right, so I've got 5 minutes to state a couple of Tim's results. Let me do that. So here's the first thing I want to say. Which is that this category of d-fold matrix factorizations is equivalent to, here's something we've seen before, maximal Cohen-Macaulay modules over R sharp bracket sigma. Where, okay, so I'm reusing symbols with new meanings. So let me tell you what everything here is. So R is S mod F. That's been true since the beginning. R sharp now is, add on a new variable Z and consider the hypersurface defined by F plus Z to the D. So these are d-fold matrix factorizations, and this is a Z to the D. Sigma now is an automorphism of R sharp that fixes S. And before, sigma took Z to minus Z. Now what it's going to do is multiply
Fine, we can allow some questions.
Sure, of course. I'll do my best to answer them
Okay.
just by talking.
Okay. All right. All right. So the floor is open for the audience to ask questions. Yeah, you mentioned the physicists being interested in matrix factorizations and your conference in overall form. So in what context, why was Dirac interested in this?
Well, so those are two different things. The matrix factorizations that physicists are interested in right now are part of string theory. So, and this is a very sort of undergraduate level understanding of string theory. What they have is certain polynomials assigned to different regions of space-time, and to pass from one region to another, you have to go from the one polynomial to the other, and the way you do that is by you have a matrix factorization of F and a matrix factorization of G minus F. You can tensor them together to get a matrix factorization of G. So that'll take you from the F place to the G place.
Mm-hmm.
So, as I say, we talked a lot using the same words and not understanding each other.
Okay. Okay. And a lot of
if I could.
Yeah.
I'm sorry, go ahead, Jewel.
No, my other question was not historical, but these matrix factorizations are related to hypersurfaces, maximal Cohen-Macaulay modules over hypersurfaces. But people do consider maximal Cohen-Macaulay modules over complete intersections.
Sure. And
so, is there a similar theory of matrix factorizations over there, which will allow us to construct these modules?
There is. In fact, Eisenbud and Irena Peva, I guess 6 or 7 years ago now, have constructed a theory of matrix factorizations for complete intersections, which does mostly what you're asking about. It has some slight differences. You don't get every maximal Cohen-Macaulay module having a matrix factorization, but you can take a syzygy or two or several to get one that does.
Okay.
So it's not quite as clean as the case of hypersurfaces, but there still is a theory in that case.
Mm-hmm.
And they have a book, I think, that details this theory.
But the factorization is still with two matrices or arbitrary number of matrices?
No, it's the let's see, the codimension plus one, I think.
Okay.
Yeah. But not, they're not factorizations like I was discussing here today. They're not just multiply them together to get f, because you now have more than one f. So the rule for combining these D plus or C plus 1 matrices is different.
Okay. Yeah. Okay, so are there any questions from audience? Graham is fortunately back with us, so
yeah, we lost some folks, I'm sure. I apologize again.
Yeah. Okay, so I don't see any questions.
Somebody raised their hand. I think.
Oh, can I ask
a
question?
Yes, please. Yes.
And the last theorem you mentioned, is there any connection about n complexes or d complexes? Usual complex in usual complex two, and if you multiply two differentials, then it vanishes. But in your case, d times differentials vanishes. So perhaps
Yes.
you know about that sort of notions, and there are some, and you in the statement is some relationship between that sort of maximal core and Macquarie modules, but you mean there are some relationship between a sort of Knorrer periodicity, right?
Yeah, this was one of the things I didn't get to mention, and to be honest, Tim is still sort of proving a lot of results that we expect to be true, but don't have all the details written down. So let me go back and answer your first question. Yes, this is very, very closely related to n complexes or d complexes, and specifically in the paper about such things. I don't remember all the authors, but there are some formulas for the syzygy of a d complex.
Yes.
And Tim was able to show that those same formulas define the syzygy of d-fold matrix factorizations, for example. And so yes, it's very, very closely related.
But maybe the interesting thing is if you focus your attention to maximal core and Macquarie module, the relationship is more how to say strong or
and
explicit.
I think there's still a lot to say here. I think that one thing I didn't mention about Knorrer periodicity is that if you do it twice, it's better behaved. That if you add on x squared and y squared, two new variables, then you can actually get stable equivalence on the nose rather than the splitting property. I think that that's true if you add on z1 times z2 times z3 up to zd, that you can still get an equivalence of d-fold matrix factorizations of f and of f plus this product. So for example, f plus xyz. So I think that this Cohen-Macaulay module's point of view really works well with this d complexes or d-fold matrix factorizations idea.
Very interesting. Thank you.
Thank you.
Actually, against your name, I see Japanese character. So would you please introduce yourself?
Oh, sorry. I'm Kiriko Kato from Osaka in Japan. I think I'm a good
I
friend
thought you
with,
were Yukiko.
with Graham. And
Thank you.
yes,
Thank
I'm working with actually a Koen modules.
Oh.
My supervisor was Yuji Yoshino.
Okay, thank you. Thank you very much. Yeah. All right.
I thought that had to be you, Kiriko, but I wasn't sure. I didn't want to offend.
Yeah, yeah.
Thank you.
Okay. Is there any other question for Graham? Well, if not, let us thank Graham for his very interesting talk and coming online to talk to all of us far away from Syracuse, but very close due to online connections. And we hope we will have his seminar again sometime in future. And just like he came to India many years ago, we hope to have him again sometime. So thank you, Graham, for coming. Yeah.
Thank you. Thank you. Thanks to everybody for showing up. I apologize again for the technical difficulties, but it was very nice to see you.
Problems. No problems.
Thanks so much.
Yeah. Bye-bye.